I'll start recording here. There is 6033 in the news. It's just coming at the end of lecture, so not right now. All right, so what are we doing today? We've been talking a lot about routing. So we've talked about the network layer, we've talked about link state routing, distance vector routing, we've talked about BGP, you've talked about RON in recitation. So we've spent a lot of time talking both about kind of the basics of network layer type routing, the types of concerns we have when we have to route across the internet. We're basically done with routing at this point. So today we're going to move up a layer in our model, and we're going to turn to the question of transport. And we're going to spend, we're basically in some ways going to spend this lecture and Monday's lecture thinking about sort of the same collection of problems. So in a way, you could think of today's lecture as part 1 of 2. And specifically today, we're going to think about how the internet does 2 things. So we're going to think about how it provides reliable transport, and I'll make that definition more precise in a second, but how it provides reliable transport in the face of an unreliable network, and also how it prevents congestion. So sort of informally, congestion happens when there are, basically when there are more packets in some part of a network than that part of the network can handle, which means that queues at switches start to build up because they're storing packets as they arrive and they can't send them out fast enough. And eventually, as queues build up, delay starts to increase. Eventually, the queues themselves will be full. It's a finite amount of memory dedicated to that queue. So packets will be dropped, right? One of the reasons that we're going to talk about these together is that in most networks, they are sort of dealt with by a single protocol, TCP. Right, so the transmission control protocol, and we're going to talk about TCP today. And so we are certainly thinking about this in the context of the internet. So we have to address issues of scale. We're also going to see some issues of sharing that we haven't had to think that much about before. So for instance, on the internet, you have like billions of people sending at once. How do we do that, right? What sort of, does anything prevent one sender from just dominating or something like that? Right? How do we share efficiently? How do we share fairly? So we are thinking about the internet in the back of our mind, but TCP, the protocol we're going to spend a lot of time on today, certainly applied to lots of different types of networks. This is not an internet specific problem. It's something we think about in a lot of places. All right, so reliable transport, what is it? All right, so our definition of reliable transport, we're going to think about having a sending application and a receiving application. We want to be able to deliver each byte of data exactly once in order to that receiving application, right? So we have our layered model over here on the right. I'm going to draw it slightly different for you on the left here. So again, you think of your sending application and your receiving application, and sort of underneath, right, one layer down, we'll think about a reliable sender and a reliable receiver. All right, that sender receiver, they're communicating across an unreliable network. Right, this is a network that can drop packets, right? Largely because queues get full. Sometimes because packets can be corrupted. There's other ways to lose packets in a network, but congestion is the big one we're going to think about today. You could even see packets in this network be reordered without loss. For instance, if the min cost route to a destination changes, like between packet A and packet B might actually end up getting there faster. All right, so we have this unreliable network, but it's going to be the job of this reliable sender and reliable receiver to get each byte of data delivered exactly once in order to the recitation. We usually talk about protocols in this world as best effort protocols. They're going to make their best effort to provide this. There is always like the very, very, very rare case that there's just a weird persistent loss and we can't get data through, but we're going to try to do our best. Right now, before we talk about how to do this, you can see on this layering on the right here, TCP is not the only transport layer protocol, right? In fact, part of our layering model lets us swap out different protocols, right? So applications can choose to run on top of TCP. Applications could also choose to run on top of unreliable transport protocols, right? UDP is an example of an unreliable transport protocol. We'll talk a little bit at the end about why they might make that choice, because there are, to some extent, you might think, well, why wouldn't you want reliability? Like, why wouldn't that be a good thing to have? So we'll talk about that at the end. But let's get a reliable transport protocol to work for us. So the basics of this protocol, it's going to work on with three different things. All right, and so here's how I'm going to illustrate it to you. I'm going to illustrate it to you in what is known as a waterfall diagram. So you can see I have a sender and a receiver here, two lines going down. These lines illustrate time. So time is flowing down like a waterfall. That's why they're called this. And this diagram is going to help us understand how packets are sent between these two endpoints. So for example, here is the sender sending a packet to the receiver. All right, I'm just gonna draw an arrow. The arrow is angled down to indicate that some time passes, right? It takes time for a packet to get from a sender to a receiver. All right, so this is the diagram. We're gonna see this a lot today. So our job, delivering each byte of data exactly once in order. First thing we need is a notion of order, right? When the receiver starts getting packets from the sender, how does it know what order they should be in? It's going to know because we're just going to tell it. All right, we're going to give each packet a sequence number. In this class, our sequence number scheme is going to be pretty basic. The sender is going to start with packet 1 and then do packet 2 and then packet 3. So they're just going to increase by 1 each time. All right, and this gives us a notion of order. So here I have my sender sending packet 1. It can send packet 2. Well, in fact, we're going to let it send packets 3, 4, and 5. So there's a bit of space between each of these arrows on the slide. That's largely so you can see them. You can imagine a network. You can imagine the sender sending out packets 1, 2, 3, 4, 5, effectively like right back to back, just like one right after another. All right. So we've sent some packets. All right. Now, in this protocol, our sender is going to be allowed to have some number of packets sort of outstanding at any given time. We're going to end up talking a lot about this, but just so you start with some vocabulary, we're going to refer that to the window size. We'll usually use W to abbreviate it. All right, so in this particular example, my sender is allowed to have 5 packets outstanding at a time. I'll define outstanding for you more precisely in a second, but not anymore. All right. For right now, you're just going to assume that that window size, it's fixed. It's a constant. It's known at the sender. It happens to be 5 on this slide. Could have been 6. I did 5. All right. So now we've sent 5 packets. This diagram illustrates to you they've all arrived at the receiver. All right. What happens next? Since we're trying to provide reliable transport, we would like our sender to know when packets have actually been received, right? Maybe said another way, we want our sender to be able to infer when a packet isn't received so they can do something different. But the way we're going to make this work is with acknowledgements, all right? When the receiver gets a packet, it's going to send an acknowledgement back to the sender. We usually call acknowledgements ACKs, right? So we'll basically never say the word acknowledgement again. We will only say the word ACK. No one has time to say acknowledgement, right? ACKs confirm that a packet has been received. So in this diagram, see something like this. ACKs are they're just packets. They don't carry any data. They're really just a header. They go back. All right, and the ACKs themselves have sequence numbers. All right, now you might look at those sequence numbers and say like, well, okay, the receiver gets packet 1 and it sends an ACK with 1. It gets packet 2, it's an ACK with 2, etc. In this protocol that we're developing, which is very, very similar to TCP, an ACK with sequence number K indicates that the receiver has received all packets up to and including K. Right? Right now, you can't necessarily tell that. There's been no loss. This is not an interesting reliable transport protocol at this point because we had 100% reliability. Right? You're going to see this in action in a couple of seconds. Right? So we've got sequence numbers, we've got ACKs, the basics of a reliable transport protocol. All right. You can design a reliable transport protocol with ACKs that work slightly differently, right? That don't necessarily indicate the receipt of all packets up to and including K. In some other classes, Kevin Live, we're going to see this in action soon. I don't like it. That was very good. Very good, Kevin. So you can design ACKs to work slightly differently. This is how ACKs are working here. It's very, very similar to how they work in TCP. We're going to exploit them in a second. All right, so we're sending packets, we're getting ACKs. What happens next? All right, So as the sender starts to receive ACKs, as it gets, you say the ACK that indicates the packet 1 has been received, it knows a couple things. One, it knows that, okay, packet 1 was received. Amazing. It also knows that packet 1 has left the network. Oh, Isaac, also very good. These puns, y'all are on it. All right, so when the sender gets the ACK for packet 1, it's going to send a new packet. It's going to send the next packet in its stream, right? Packet number 6. And now I can define more precisely for you what it means for a packet to be outstanding. Outstanding just means it hasn't been ACKed yet. So the sender sent packets 1 through 5, right? Hadn't gotten an ACK back for any of them yet, so just kind of hung out. Once it starts receiving ACKs, it can send more packets. This means that the window of outstanding packets, initially it was 1 through 5. Now it's 2 through 6. If there's no loss, it would then go on to be 3 through 7, 4 through 8. All right, as a result, this is known as a sliding window protocol. The window of unacked packets slides along the sequence number space, right? So sliding window protocol. Now let's make things more exciting, all right? Let's introduce loss. Well, we'll get an ACK at some point in the future for that packet. So we're gonna say packet 7 gets lost. What is this protocol gonna do? All right, let's, we're gonna assume, okay, packets 8, 9, and 10, they happen to get through. We're still gonna have to deal with the loss for packet 7. One thing to notice about these packets though, here you can see that the sequence number on the ACK's kind of in action. Oh boy, this is gonna go badly for me. And you can see that, oh, the sequence number space on the ACKs isn't advancing, right? It stays at 6. Packets are still getting through, they're still getting ACKed, but the receiver has only received all packets up to and including 6, hasn't gotten packet 7, right? Now, certainly what we want here, like looking at this from kind of an like omnipotent standpoint, the sender needs to resend packet 7, all right? It just does. It got lost in the network. It needs to send it again. And we're going to find that there are a couple of mechanisms that can get that to happen. But one of them, the kind of very basic one, so eventually, we send packet 11, we get an ACK for it, is a timeout, right? So every time the sender sends a packet, it sort of starts a timer, right, that says, I'm expecting to receive an ACK for this packet within timeout number of milliseconds. If I don't, I'm going to resend the packet. All right. That is what I am illustrating for you here. Right. This is not the only way that we see loss in a network. This is not the only way we see timeouts kind of kick in a network. So before I talk in more detail about this timeout, let me just show you some other bad things that can happen. Right. So we can lose a packet. We can also lose the ACK for a packet. All right. So now, if you're looking at this diagram, you, students, can be very alert and you could say, ooh, something's different here, right? One of the things that is different here is that when only the ACK is lost, not the packet, that sequence number space looks different. Sequence numbers on the ACKs start to advance in a way that they did not before. Before they just were 6, 6, 6, 6, 6, right? We're going to come back to that, but it's still certainly possible that the timeout for packet 7 might fire before that happens, right? That can happen. So that's what you're seeing here. Another thing that you might see on a network is not actual loss, but a change in delay. So for instance, packet 7 gets here, but all of a sudden the ACKs back, they just start to take longer, right? Path change in the network, they're more congestion, whatever, right? So we could certainly see timeouts fire again, have the sender retransmit packet 7, right? In this case, this is known as a spurious retransmission. And so, the sender retransmitted a packet that actually wasn't lost, just thought that it was lost, right? So these are sort of all of the ways that some of the ways we can see bad things happen in a network, right? Now, if we had some additional time to talk about reliable transport, if we had maybe like 3 lectures on reliable transport, we could spend a whole chunk of time just talking about this timeout, right? What should that timeout be like, all right? Certainly, we don't want it to be too long, right? If I have like a 10-second timeout to retransmit a packet, wait forever, right? That's so long. But 10 seconds on the internet is basically forever, right? It's like, 50 to 100 milliseconds to get packets from Boston to California and back. All right, so 10 seconds would be forever. At the same time, if it's way too short, right, like if that timeout is really, really small, even smaller than, say, the round trip time of the network. The round trip time here is the time between sending a packet from the sender and getting the ACK back. All right, if it's too small, our sender is going to be doing all of these spurious retransmissions. It's going to be putting like twice as much data into the network as it needs to be. So estimating that timeout correctly is actually a huge part of these protocols. TCP does it in a decently smart way. It basically estimates the average round trip time, and then it also estimates a measure of variance of the round trip time, because round trip times are never constant, right? And then says, I'm going to set the timeout to be a little bit larger than sort of average RTT plus some function of the variance, right? That's a very high level description. What I want you to take from it is that setting that timeout does actually matter, right? Now, I've talked a lot kind of about what the sender has to do here, right? It's keeping track of timeouts, it's keeping track of its window size. The receiver is kind of the less complex entity here. All it really has to deal with, it's going to ACK every packet, and it needs to suppress duplicates. So for instance, you can see here our receiver received packet 7 twice, right? It doesn't want to deliver packet 7 twice to the application. So it just keeps track of sort of the packets that it sent to the application. It's not going to send duplicates. It's going to deliver them to the application in order. Again, it has the easier job of between sender and receiver, right? This is the basics. This is the basics of a reliable transfer protocol. Put sequence numbers on your packets to give them an order. Receivers send acknowledgements, right, when they get a packet so that the sender can infer loss. And use timeouts to retransmit packets. If you think you should have gotten an ACK back by now and you haven't, send the packet again. Sometimes you end up sending a packet when you don't need to, but hey, all right? So, but it's like 2:22, right? We're not done with lecture. It's because we kind of have a bigger question to answer, right? This value W, like 10 minutes ago, I said, it's just 5 here, it's fine, ignore it, just let it be 5. We can't really do that in the internet. We have to ask a much more important question. In this protocol, what's the correct value of W? Why does this matter? Right? Well, if W is very, very small, right? Say that I'm working with a network that could handle 1 million packets per second. And I'm putting in like 1 packet every second. Well, it's a very underutilized network, right? There's room for more. We don't want to do that. At the same time, if our window size is too big, we're going to end up adding a lot of congestion into the network, right? So let's think for a second, what do we even feel like it should be? All right, so I'm going to give you an example. Draw some pictures. Move that pen. All right, so we're going to have, here's my sender S. Going to send through 2 switches that I'm not going to give a name to some destination D. All right, so here's my network. I've got it set up. There's 1 sender, 1 destination. Traffic is just going this way. And let's say, maybe this link and this link very, very fast. This link here is going to be my bottleneck link. You've heard the term bottleneck before in this class. When we talked about performance. So this is the part of our system that is going to limit performance. All right, I can zoom in a little bit. There we go. All right, so let's say in this example, let's say this link is capable of sending 100 packets per second. All right, and we'll even imagine that the round trip time, so the RTT, is 1 second. We're just going to make the math like as easy as possible. Okay, so here's what we're going to work with. In an ideal world, well, we would like S to be putting in 100 packets per round trip time, right? This link can handle it. We'd love to see W set to 100. All right, now we could already ask ourselves one question here. How would S know this? There's not like a part of the system that automatically tells you this is what your bottleneck link capacity is. Right? So S would have to infer this some way. But I'm going to sidestep that question for you because I'm going to make your life more difficult for a second. We're going to keep the exact same network here, but now someone else is going to show up. All right. And this is a second sender sending traffic to a different destination, but they're going to share the same bottleneck. Right. So we're sending traffic this way and traffic this way. So if both of these senders say, hey, bottleneck link, the capacity is 100 packets per second. I'm going to send my window size to 100, things are going to go great. All of a sudden, this switch here is getting 200 packets per second. It can't handle that, right? It's not capable of that. It can't get them out of its queue fast enough. Queues are going to build, packets are going to be lost. All right. To say nothing of what happens if like S3 shows up and then S4, right? This is our big issue, right? How are we going to do this? All right. So first thing, what do we even think we want to have happen? All right. In this example, maybe we imagine that, okay, actually with two senders, we would like to have this happen. Right? We'd like them to both cut their window in half so they're both getting the same amount of data through this network. All right. How will they know to do that? They don't know about each other, right? How will they know to make this adjustment? What will they do when S3 comes in? Or what will S do when S2 leaves? What will they do if the bottleneck changes? Right? There are all of these questions. And this is what we're going to try to answer today. How can our reliable senders, using this sliding window protocol, set their window size in the way that we want them to, right? We want them to maximize utilization. We want our network to be fully utilized, but we don't want congestion. We want things to be fair, but there are all of these other endpoints in the network. There are all of these different changing demands, right? And think about this on the internet. We have to get senders to sort of collectively behave, right? There's so many of them, and we don't want them to overwhelm any part of the internet, right? So how will we do that? Okay, so the mechanism that we use to solve this problem is known as congestion control, all right? So congestion control basically means we're going to control the source rate, so the rate at which these sources or senders are sending data, to try to achieve high performance. All right, in our case, we want efficiency and we want fairness. Okay, so what does this mean? Right? What does it mean to be efficient? Well, we want a couple of things to happen. We don't want a lot of packets to be dropped. We want as few drops as possible. We don't want delay, right? We don't want those queues to build up and build up. Even if they're not dropping packets, it means my packets have to wait behind a lot of other packets in a queue. I don't want that. But at the same time, I want to utilize the network as much as possible. If that bottleneck link can handle 100 packets per second, I'd like to be putting 100 packets per second into it, right? Like, it is not a solution for us to say like, well, just don't use the network very much. We want to use the network a lot, right? We just don't want other bad things to happen, right? So we care about efficiency. We also care about fairness. Fairness is really tricky to talk about. I'll say more about why that is later on in lecture, but we're going to go with a starting definition for now. I'm going to put it on the slide, and it's probably not going to make a lot of sense yet. All right, so under infinite offered load, we're going to split the bandwidth evenly among all sources sharing a bottleneck. So what does this mean? Infinite offered load is one of my favorite phrases in networking. It just sounds cool. Infinite offered load just means that we're going to assume that all sources have infinite amount of data to send. And this probably sounds like a kind of a wild assumption to make. Like, why would I want that? Why would I want so much data? What we're trying to get at is that if my sources have an infinite amount of data to send, they always have a packet ready, right? If I allow them to send, they have something to send, right? This is actually a pretty decent way to model kind of like a large, especially long running connection. There's always a packet ready and waiting, right? One of the reasons that we want that is because with that assumption, we can take a particular definition of fairness and it makes sense for us. So assuming that everybody always has a data to send, we're going to split the bandwidth evenly among all sources that are using the same bottleneck. So my example before with S and S2, we split the bandwidth in half, right? The amount of data that they could send in half. If we were all sharing a bottleneck link, so there's 168 of us right now, and we all have infinite data to send, we are all going to get 168th of that bottleneck link bandwidth in theory. All right, so this is what we're going to work with for now. We'll come back to fairness. We're going to go with this for now. All right, so the particular type of congestion control that we're going to study today, it's an end-to-end congestion control protocol. All right, sometimes known as a window-based congestion control protocol. The idea behind these types of protocols is that the switches in the middle of the network are dumb. All right, all of the switches can do is drop packets. They're not going to help us out in any other way. The sources are smart. All right, sources can adjust their rate to converge at the optimal rate. For us in TCP, that means our sources are going to be able to adjust their window size. This window size is not fixed. It's going to change all the time, right? And the basic strategy I can give to you in one sentence. The basic strategy is that senders are going to increase their window size until they experience congestion. Then they're going to back off. They're going to decrease their window size, and then they're going to try again. All right, so they're going to go through this kind of increase, decrease, increase, decrease. All right. The reason to kind of cycle there is because that, that correct window size, it keeps changing. The link that is your bottleneck can change. The number of sources sharing a bottleneck can change. Right? There's not going to be one set window size forever. Right? How they increase, how they back off, that's coming. That's the whole thing. Right? But how are sources going to know that they're experiencing congestion? Like, how are they going to know that there's a problem? We need some sort of signal for congestion. There are a lot of things that happen when there is congestion in a network, right? So I'm sending a lot of packets. I'm sending too many packets into the network. Queues are starting to build, right? Which means I'm starting to see latency increase. Delay in the network is increasing. I'm seeing throughput kind of leveling off, right? I'm not getting any more packets through. And then eventually our senders are starting to see loss, right? Packets are being dropped. That is the signal we're going to use for congestion in the network, right? Packet loss in the internet, in most parts of the internet, reliably signals congestion. It's rare to lose packets to something like corruption, right? It is also a binary signal that's easy to interpret. It happens or it doesn't, right? A packet was lost or you got an ACK for it, right? For the most part. Estimating like delay, like seeing if latency is growing, that's a little bit harder. It's a noisy measurement. Round trip times vary all the time on their own. So we're going to deal with packet drops. All right. So the basic idea behind TCP congestion control: increase your window until you see packet drops, and then back off and try again. All right. So here's how this will work. I'm going to draw this first for you on a blank graph, and then I'll give you a nice graph with that it's not messy. So we're going to start. We have a window size. It's really small, like a window size of 1. All right, so we put one packet into the network. Say that I'm sending data to Sam, because Sam, you're next on my Zoom today, so you get to be the receiver. So I'm sending data to Sam. I send him one packet. I get an ACK back for it. There was no loss. Here's what I will do. I'm going to increase my window size to 2. All right. I'm going to try sending Sam 2 packets. All right, so I'm going to send them like back to back, one right after the other. All right. Suppose there continues to not be loss. All right, I get 2 ACKs back from Sam. Wonderful. I'm going to try 3. And as long as there's no loss, I'm just going to keep increasing linearly. So I'll go 4, 5, 6, 7, 8, 9, 10, however many dots I got up to here. All right, and let's say, so let's do 10, because I think that's what's on the next slide. Say I send 10 packets to Sam, and now there's loss, right? Either I don't get an ACK back from him, so I infer, there's loss. The thing I will do next, there's a lot of options, right? Maybe I subtract 1 or something like that. I'm going to cut my window in half. All right, so it's going to go from 10, say, down to 5. And then I'm going to continue on with this increase, decrease. All right, this rule has a name: additive increase, multiplicative decrease, right? AIMD. So every round trip time, if there's no loss, right, we increase our window size by 1. When there's loss, we cut it in half. All right. So the increase rule is additive. The decrease rule is multiplicative, right? Multiplying by half. Right. So you'll see graphs like this. This is a nicer version of what I drew for you. Although notice that in this example that I've given you, things start to go down. Right. So what might have caused that? Right. Well, imagine in this process, I'm sending data to Sam, right? I'm getting my window size goes up to 10. Then I see drops, it goes down to 5, and I increase. And let's say all of a sudden Karen comes in the network. Karen is third on my Zoom today. And she starts sending, maybe she's also sending to Sam, or maybe she's sending to someone else. But either way, Karen and I are sharing a bottleneck link. All right. Now I've got to kind of compete with Karen. Right. So as we collectively put, say around 10 packets onto this link, we're both going to start to see loss, right? So I'm going to cut my window back in half. Like maybe I start to see loss when I've put in, say, 8 packets, because maybe Karen has already put in 2, right? And so that's how you would start to see things change, right? So that's how you'd start to see something like this decrease, right? Another sender shows up, right? If Karen leaves, she's done sending, my window size will pop back up. Right. So this is the basics of the version of TCP that we're going to study in class today. Right. So when I learned this as a student, I thought this seems fine. Like that was my assessment of this protocol. Seemed fine. I sort of got intuitively why this might be a reasonable thing to do. Senders are sort of conservative about their increase rule. It's safe. And then they back off really dramatically when there's loss. So like, okay. The thing is, a lot of the stuff around TCP is backed by a lot of very nice math. So if you're interested in math, you can read all about it in some of the original TCP papers. But I'm going to try to convince you to some extent that this particular rule is not arbitrary. And that in fact, it gives us a chance of meeting our efficiency and fairness goals. All right, so we're going to do this in a type of graph that we've never seen in this class. You got waterfall diagrams, you got TCP sawtooth diagrams. Now you're going to have more things. It's a big day for all of you. All right, here's what we're going to look at. Imagine 2 senders, S1 and S2. They are sharing a bottleneck link. All right, you can imagine it's me and Karen sharing a bottleneck link. We're both sending at some rate. Right? Like our window size over a period of time, right? What do we want? What do we want our rates to be? Well, we care about efficiency, all right? I want that bottleneck link to be full. I want S1 and S2 collectively to put as much data as that bottleneck link can handle. But there's a lot of different ways to do that, right? Assume that the bottleneck link can handle like a rate of B packets, we'll say per second. All right, per round trip time, doesn't really matter. All right, yeah, I could have S1 send B packets per round trip time and S2 send none of them, or vice versa, or they could land somewhere in the middle, right? Anywhere along this line, anywhere where their rates combined are equal to B, that's an efficient network. If we're below that line or kind of on the left side of that line, we're underutilized. We're not putting as much data into the network as it could handle. If we're living above that line, the network is starting to get congested. I'm putting more than B packets per round trip time, per whatever unit of time into the network. The queues are going to start to grow, right? Packets are eventually going to get dropped. So I want to live somewhere on that line, all right? But again, imagine Karen and I are sharing this network. Karen's not going to be super happy if the answer to this problem is like, well, I'll put in B packets per round trip time, and Karen, you just don't send anything. Right? That is an efficient network, but it's not a particularly fair network. All right, so fairness for us, we want these 2 senders to be sending at the same rate, right? We're assuming infinite offered load. We're just going to try to split things equally, right? But again, there's also a lot of different ways to do that, right? If Karen and I both put no data into the network, well, fair to some extent, right? If we both put like 1 packet per round trip time, that fits our definition of fairness. So anywhere along this line where these 2 rates are equal. right? Now, you can imagine, given this graph, you kind of know where we want to be, right? Not here. We don't want to be in a world where S1 is sending more than S2, nor do we want to be in a world where S2 is sending more than S1. We want to live here, right? The network is fully utilized and things are fair, right? What I'm going to try to show you is that AIMD gets you there, all right? Again, there are two senders. They have infinite offered load. This is a very, very, very constrained example, but I think it's an interesting way to think about it. So a fun thing you can do, take this diagram and you like just throw a dart at it and pick a point. Okay, we're picking this point because I made the slides ahead of time. All right, so we happen to be living here. What's going on here? S1 is sending, it looks like a little bit more than B over 2, right? Sort of in there. S2 is not sending very much data at all, right? Perhaps S1 is kind of, it just cut its window in half, it's building back up, and S2 just entered in. But certainly we're living on this underutilized world in this graph. We're on the bottom side of that pink triangle. So, okay, there's not going to be loss. Both senders are going to increase their window size, right? They're going to see this linear increase. So we're going to move from this point linearly, right? They're increasing their window size by the same amount. We're still underutilized. We're going to see this happen again. Still underutilized, no loss. It's going to happen again. Now, at this point, we've gotten over this line for utilization. Typically in a network, though, there's going to be a little bit of a delay. Queues are going to start to grow, but packets aren't being lost yet. So, we might see S1 and S2 increase again, but eventually they're going to start to experience loss. Eventually, they're going to cut their window size in half, right? And there is a nice geometric way to find out where that is on this graph. We're going to draw this line back to the origin. Halfway point of that line, right? That cuts both axes in half. Right? Geometry, you weren't expecting it, and here it is. Geometry always comes when you don't expect it, right? So now we're here. And now this process is just going to repeat. Underutilized, increasing. Eventually we get far enough over that line, cut in half. We keep going, we keep going. And as you can see, we are moving closer and closer to that fixed point, right? And eventually we will sort of oscillate around it, right? Now compare this to a different rule. Suppose my rule had been additive increase, additive decrease, which would have said something like increase your window size by 1 until there's loss and then decrease it by 1, right? So we would have started here, moved additively, and then just moved backwards, right? We would have kind of been living on this line. We would have not moved close to that fixed point, right? So additive increase, multiplicative decrease can try to get you there. Right now, this is not a proof. I picked one point and did one illustration. Weekend's coming up. You could print this out, throw darts at it, do it from any point. You're going to get to the fixed point. All right. So this is kind of some of the intuition between why we would use additive increase, multiplicative decrease. Right. However, we've been operating in kind of a perfect world. All right. We imagined a world with infinite offered load. All right. That's not always the case. Right? Let's imagine, okay, Karen and I are sending into the same bottleneck, and Felipe is also joining us. All three of us are sending to the same bottleneck link. That bottleneck link can handle 100 packets per round trip time. We all have the same round trip time, right? But let's say that my application, it's only generating 20 packets per round trip time. Like I don't have more data to send, right? What's going to happen? Well, we can all start off, we'll start increasing our windows. We'll all get to 20 packets per round trip time. That's fine. We haven't overutilized the network, but my sender is good. I can't generate more packets, so I'm just going to kind of stay at 20, and Felipe and Karen will start to increase, right? In theory, they should get up to 40, and they'll start to see loss, right? Back off, things like that, right? This, if that happens, that is a fair allocation in some sense, right? That is a sort of a max-min fairness. Right. So even when we don't have infinite offered load, we, in theory, still get some fairness here. In practice, that might sort of happen, or things might be worse. Karen might have this crazy long round trip time compared to Felipe's, right? So long. She's not going to increase her window at the same pace, right? In terms of absolute time, it's going to take her longer to increase, right? There's all of this oscillation. It is complicated to make like definitive statements about fairness in this arena. It's hard to talk about it under skewed workloads, which we see all the time. Skewed workloads just means different senders have different amounts of data to send. Hard to talk about it when round trip times vary, which they totally do all the time, right? So it's tricky. All right, so this is kind of the main part of this particular version of TCP congestion control, but there are a lot of other mechanisms at play here. So I'm going to talk to you about two of them. All right, so let us go back to this graph. All right, so looking at this graph, one thing that you might notice, this phase of the graph kind of takes a long time, right? For some reason, I've started it at 0 instead of 1, but you could really imagine the window size starting at 1. It takes a while to get up to sort of to get the network fully utilized, to get going. If this is a long running connection, who cares, right? My connection is going to be running for a really long time. I don't care about that starting portion. But if I have a very short connection, this might be kind of annoying, right? And in this graph, I got us kind of up to congestion in 10 round trip times. On a real network, we would expect that to be quite a bit longer, all right? So TCP comes with a fix for this. The name is going to be surprising, all right? The fix that TCP gives you is at the start of the connection, double the window size, all right? So instead of this linear increase, you see an exponential increase, all right? So instead of doing 1, 2, 3, 4, 5, we're 1, 2, 4, 8, 16, right? Until we see loss. The name is surprising, right? The name slow start, because it's like the point was to be faster. The reason it is called slow start, when it sort of came about, the competing idea was at the start of a connection, just blast all of your data, see if you get any loss, and then back off. So this was slower than that. But in the context of things now, this helps us sort of get connections started faster. And it's really great for kind of really small, short connections. It gets their data into the network and done faster, right? So this is one optimization. The second one is my favorite of the two. All right, so you already know that in these reliable transfer protocols, we have a mechanism to retransmit packets after a timeout. That's what we talked about at the beginning. All right, but let's look at this picture again. This is the same picture you saw at the beginning, except I made one addition. I changed the timeout to be really long for packet 7, right? So you can see here, I got quite a bit of delay between retransmitting packet 7. But look at those acts. Those acts tell you something, right? They tell you that something has happened to packet 7, right? We're constantly seeing acts that say, hey, I've gotten every packet up to and including 6, but not 7. And yet we're still seeing subsequent acts. Other data is getting through, right? Packets 8, 9, 10, all of that data got through, right? TCP exploits this, right, with a mechanism called fast retransmit, fast recovery, right? So as soon as it gets these 4 acts in a row, it's going to go ahead and retransmit the relevant packet right away. It's not going to wait for the timeout to expire. Common terminology you will hear is to talk about these 4 acts as sort of the original act and then the 3 duplicate acts or dupe acts. No one in networking has time for multiple syllables, so we don't say acknowledgements, we don't say duplicates, right? We 1 syllable at a time, right? So this method is actually really great when there's only like an occasional packet loss. Just retransmit packet 7, go about your business, right? But think about what's going to happen if there is a great deal of loss, right? Imagine that all of these packets also got lost, right? One thing we would start to, we wouldn't see all of these repeated acts, right? We wouldn't get all of those duplicate acts in time, all right? And in that case, yeah, packet 7, the timeout will expire and packet 7 will go. All right, so let's talk about what that means in a network. So first of all, in practice, if only one packet is lost, you are going to see those duplicate acts before the timeout expires. RTO stands for retransmission timeout. All right, so if just a single packet is lost, you're going to get those 3 dupacks, you're going to retransmit, everything's going to go pretty well. If a timeout actually expires for a packet, it usually indicates a great deal of loss on the network. Like packet 7 got lost, and packet 8, and packet 9, and packet 10, like a lot of packets in a row got lost. Right? Because you didn't get those duplicate acts, other packets weren't getting through behind the first one that was lost. So TCP, despite 4 is not specific to this example. Why 3 dupe acts? My guess would be experimental data. I'm going to let some other staff members weigh in and see if they have a more mathematical answer to that. But no, it's not just to this specific to this example. So when a timeout expires for a packet, TCP actually interprets that as huge loss on the network, and it does something slightly different than what I have told you. I've been lying the whole time, right? When there is a retransmission due to the timeout, TCP will drop its window all the way down to 1, right? Then it will do some slow start till it gets up to roughly the last good window, and then it starts its additive increase again, all right? So in some ways, TCP interprets that event of big loss almost like it's restarting the connection to some extent, right? This is part of the reason why it really matters to try to avoid loss on the network, because TCP will react quite harshly to this. We will sometimes see this come up in other areas of systems. So if you have a connection that's kind of going up and going down, you'll get stuck in these slow start cycles, and it can really kind of throttle your connection. You won't be sending as much data through as necessary. All right, so we have 3 minutes left to reflect. TCP, in many ways, it's been a massive success, right? The internet basically wouldn't work without it, without congestion control, right? But there are some really interesting questions. We talked about this in the first lecture. Why is congestion control coupled with TCP? And is that the right thing? Why not make it its own layer, right? There are also, there are some other things to say about this. In certain types of networks, TCP's congestion control can actually make problems like drops, delay, and things like that worse, right? It is really hard to talk about fairness in practice and to think about, is this fair? How do we decide? AIMD is also not the final word here. There's actually been quite a lot of exciting research in the congestion control arena recently, like in the past decade or so. More modern versions of TCP, they take the same approach in the sense of like increase your window until there's loss and then decrease, but they make different choices about those increase and decrease rules, right? So there's a lot of interesting work in this arena. And then one of the things that I want to leave you with before I kind of prep you for Monday's lecture, so many people did a lot of work in the early days of TCP. So a lot of this comes from a paper by Van Jacobson, but I just wanted to call out one researcher in this area who I was just a super fan of. Her name is Sally Floyd, and unfortunately she passed away about 1.5 years ago. I never got to meet her. I really wish I could have met her because she did this stuff that I was like super interested in grad school. But I was looking at her, her obituary today, and this one quote just really stood out to me, right? So talking about her work on congestion control was about keeping it working for everyone. So thinking about how would this work for people with fast connections, for people with slow connections, right? Maybe for people with long round trip times, for short round trip times. And I just think that, we often look in this class at who makes choices and who those choices affect, right? How TCP congestion control works matters. And here is a person who kind of explicitly designed for fairness. I just think it's really cool. She was just an amazing researcher. And I just wanted you all to know about her because I was a huge fan. So I'll put a link to this on Piazza so you all can read it as well. So let me lead you. I told you this was part 1 of 2 for lectures. This is all we're going to say about TCP in lecture. Here's one lingering problem. Let this sit with you over the weekend. TCP's congestion control mechanisms don't react to congestion until it's a big problem. TCP doesn't do anything until packets are being lost by the network. All the while queues were building up, delay was increasing. All right. So one thing we're going to think about, can we get senders to react before queues are full? Could we somehow say to senders like, whoa, 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 just back off. Like we haven't seen packet losses yet, but we're going to, please stop sending. All right. So that's what we're gonna talk about on Monday. We're gonna talk about some other work that Sally Floyd did in this area, which is cool for me. But that is it for TCP in lecture. So let me stop sharing and stop recording.